Welcome back. So now what we're going to do is look at multi-agent systems where we don't get to observe the state of the world. This is called partial observability. So let's look at one case. First of all, we have partial observability in a computation. Now suppose we have this goal kick here. So we have a soccer game and the kicker gets to choose whether to kick right or left. So this is the goal penalty shootout. So there's one kicker and the goalkeeper. And the kicker either gets to choose right or left, and the goalkeeper doesn't have time to wait till he's seen what the kicker's going to do, so they have to decide up front whether to jump left or right. And suppose the probability of a goal is given in this table here. So if the kicker kicks left and the goalkeeper kicks left, the probability of a goal is 0.6. So they've basically both gone different directions. So the kicker kicks left and the goalkeeper kicks right, so they both go in the same direction. Then the probability of a goal is 0.2. And similarly now, if the kicker kicks right, the goalkeeper kicks left. So then they both end up over here. The probability of a goal is 0.3. If the kicker kicks right, so the kicker kicks to there, and the goalkeeper goes to their right, which is go there, the probability is 0.9. Alright, so let's try and work out what each agent should do here. So let's think about this. So the kicker looks at these things and says, it seems though right is better because 0.9 is better than 0.6 and 0.3. The goalkeeper kicker's trying to maximize. The kicker is going to say, let's go right. Looks better today. The goalkeeper's going to think, they're going to go right, so I want to go left. And then the kicker says, they're going to go left. So the kicker says, I want to maximize, so I'm going to go left. And the goalkeeper says, if they're going to go left, then I want to minimize, so I should go right. And then the kicker says, if they're going to go right, they want to maximize, and I should go right, and we're all back to where we started with, and we end up with a cycle. So we end up with this cycle of reasoning about what the best thing to do is, and you can't work out what to do is. So there's no way of working out what the right reasoning about thinking. You keep changing all your actions. You keep just in this game here, you just keep alternating and thinking, I should go right, then I should go left, I should go right, I should go left. So it's not very useful. Alright, so instead of doing that, what we're going to do is we're going to consider a stochastic policy. So we're going to go right with some probability and left with some other probability. So the kicker's going to kick right with some probability, and the goalkeeper is going to jump right or left with some probability. Okay, so that's what we're going to do here. So we're going to go to here, and now we're going to look at this case here. So now what we're going to do is the kicker has the probability of the kick right. They can kick right with probability 1, or they can kick left with probability of 0. And then we can plot the probability of a goal. Well, the probability of a goal depends not only the probability of the kicking, but the probability that they will jump to the right. So this says here, so let's look at one of these cases here. So this says that 0.9 is the probability of a goal given the kicker kicks to the right. And the person jumps to the right. If they kick to the right, the person jumps to the left, the probability is 0.2. If the kicker kicks so this is the probability of the jump to the right, so they jump to the right and they kick to the left, probably 0.2. And this one here is they both go left is the probability of 0.6. So if we do as a function of the probability, you notice that all of these are straight lines. And it has this very interesting property that it all crosses in the middle of this point here. And this point here is a significant point where they all cross. It's basically saying, well, if I'm at kick 4, if the probability that K is 0.4, then it doesn't matter what the jumper does. The jumper can't strategize to defeat them. So if any time the kicker deviates from this, they go away from this, then the person who's jumping can deviate can sort of do something else. So this is the maximum value that the kicker can guarantee to get. Any deviation from this probability, the jumper can do something to defeat them. So this is a special point here, and it's going to be called a Nash equilibrium. So this is the point here where there's no point in the kicker is not rewarded for deviating from this. And it turns out it actually doesn't matter what the person who's jumping does. In 3 dimensions, it actually looks the same from the other way around, and so they actually both get to the same thing. There's this one point in here where no one is rewarded from deviating from this policy. All right. So let's have a look at what's going on here. So assume a general n-player game. a strategy for an agent now is a probability distribution over the actions for the agent. So it's not just a selection action, but it's a probability distribution over the actions. So strategy profile is an assignment of a strategy to each agent. So now we have a strategy profile, we're assigning a strategy to each agent, and the strategy is this probability distribution over actions. So strategy profile sigma has utility for each agent, and we can actually work out what it is because everything is now well defined. If we have probabilities, there's only just utilities involved there. There's no decision. It's just a normal probabilistic inference. And we're going to let utility of sigma I be the utility of strategy profile for agent I. So that's what we're going to do. So this utility of strategy profile is an assignment of a probability distribution for each agent, and I is the agent. And we're going to use this funny notation. If I is a strategy profile, sigma I is the strategy for agent I in sigma. And then we're going to do sigma minus I as a set of strategies for the other agents. So we're going to view this sigma, the strategy profile, as for agent, this is the distribution for agent I, and this is the one for all the other agents. Alright, so now we're going to define it. So sigma I is a best response to the other player's strategies. So we're going to now fix the other player's strategies if for all other strategies that the agent I could do, the utility for this one's greater than or equal to it. So it's not as though, so this agent here, so given the other agents, this agent can't do better than selecting sigma I. And that's called a best response. So this is the best thing it could do. It's a best response. It's one given sigma I minus 1. You know, as far as sigma I is concerned, it might as well choose this one as any other one. That's called a best response. So then a strategy profile is a Nash equilibrium if for each agent I, the strategy sigma I, the strategy in that Nash equilibrium is a best response to the other players. So a Nash equilibrium is a strategy profile that no agent can be better by unilaterally deviating from the policy. If everyone else is following this policy, there's no advantage in one agent from deviating from that policy. And that's going to be important. And it turns out that, that John Nash in 1950 proved this very important theorem that says every finite game has at least one Nash equilibrium. And that was sort of very significant because it gave us the mathematical tools in order to model multi-agent systems. It seems like a reasonable thing to do, so you don't want to have something you're not going to deviate from. And it's one of the few situations where there's always exist ones, and that's actually important for a lot of theoretical understanding of games. So it turns out Nash equilibrium have been very influential in the development of games and economics. Alright, so it turns out there can be multiple equilibria. So here's a game here of agent 1. So there's agent 1, basically it's sort of like there are two agents. One can act like a dove, be very peaceful, and one can act like a hawk and attack. And agent 2 can also act like a hawk or a dove. Okay, so if the agents both act like doves, then then they get to share this resource. R is the value of a resource they get to share. Maybe it's a piece of something to eat. Or maybe it's a country that would go an oil field that we might invade. So if the agent 1 acts as a hawk and agent 2 acts as a dove, then agent 1 gets the whole resource and agent 2 gets nothing. Similarly now, if agent 2, so if agent 1 gets to act as a dove and agent 2 gets to act like a horse, then agent 2 gets the whole resource. And otherwise you get mass destruction. If they both act violent, if they both act like hawks, they both fight, they both hurt each other, and we're going to assume here they both lose some value D. Okay, so that's the story here of this hawk-dove game. And why this is interesting is there are multiple Nash equilibria. In particular, this is a Nash equilibrium. If you're at this position here where agent 1 is a hawk and agent 2 is a dove, then agent 1 has no incentive in order to act like a dove, because then they only get half their resources. Agent 2 has no incentive to act like a hawk, because then they go from 0 to minus D. So this is one Nash equilibrium. As one agent acts like a hawk and the other agent acts like a dove. Another one is this is another equilibrium. Again, no other agent can improve themselves by unilaterally deviating from this policy, from that policy. So agent 2 loses by becoming a dove, and agent 1 loses by becoming a hawk. So it turns out there are three Nash equilibrium here, And there's also a Nash equilibrium due to symmetry. That is the case about where they both act randomly and there's some chance of destruction. So there's some chance of acting like this. And people use this game to actually explain sort of politics in different regions about how different superpowers act. Alright. Okay, so there's actually three multiple equilibrium. But multiple equilibrium don't only arise because of competition. So here's another one. So here's another one, a coordination game. So agent 1, they have to decide, we both have to decide whether to go shopping or to football, and agent 2 also gets to decide shopping and football. And in this scenario, agent 1, if they both go shopping, then they're happy, they get an action of, they get a reward of 2, and agent 1 gets gets a reward of 1. If they choose different things, then they both get 0. So none of them they both want to do the same thing. It's just that agent 1 has a preference for shopping and agent 2 has a preference for football. And so in this case here, they both have to choose something, but they're both actually choosing something simultaneously. It doesn't actually mean we know what to do. So agent 1 doesn't know whether to football or shopping, because they both have to choose simultaneously whether to go shopping or football. They both have to choose one of these two things. And therefore you want some coordination. But in here there are again actually three. There's actually another equilibrium which has randomized strategies in here, which has a chance. These randomized strategies has a chance you'll end up in this one where they're both very unhappy. So here's the case about it's a coordination game. They both want to coordinate. They both want to be together. They just have slight preferences for things. And doesn't mean they know what to do. So that's one problem with a Nash equilibrium. Not only their multiple Nash equilibrium, but given their multiple Nash equilibrium, it doesn't actually tell us what the agent should do. All right. So here's a famous case of Nash equilibrium, and is the instance of it I like best. So there's two strangers who are in a game show. Okay, they each have a choice. They can take $100 for yourself, or you can give $1,000 to the other player. And you're assuming you're never going to see that other player again, so you can't sort of ask for it back or to split it. You basically either taking it for yourself or giving lots more to the other player. Okay, so this can be depicted as this playoff makers. If player 1, if they both take, they both get 1,000. If they both give, they both get. So if they both take, they both get 100. If they both give, they both get 1,000, right? But if player 1 gives and player 2 takes, then player 1 gets 0 and player 2 gets $1,100. And here, again, if player 1 takes and agent 2 gives, then they're going to get 1,000. So this seems like the obvious solution is it's much better off if they both get $1,000 and they both get $100 or they both get 0. But if we look at what happens with the Nash equilibrium here, player 1 looks at this case here and says, well, I'm getting 1,000 here, but if I take, given that the other player is going to give, then I can increase them. So player 1 is going to look at this and say, I'm better off by doing this, because their 1,100 is better than the 1,000. So they're going to say, I'm going to deviate from, so this is not Nash equilibrium because player 1 is going to deviate from it. And then if player 2 can think, well, if they're going to give, if they're going to take, I'm better off taking too. So you end up in this. So it turns out this is the only Nash equilibrium in this game. They both take, and it doesn't result in the best outcome for either player. Okay, so they're both, being selfish and trying to just to maximize what you're trying to do doesn't necessarily give you the best outcome. You might think that it does, but it doesn't. So this is a simple example of doing this about where player 2, but it's much better. The best outcome is you both get 1,000, but the only Nash equilibrium is you both get $100, and so you're both worse off. Right. So here's another example of this. It's called the Tragedy of the Commons. It's sort of a much more agent version of the prisoner's dilemma. There are 100 agents, and there's a common environment that is shared amongst all the agents. So each agent has a 1/100th of the shared environment. Okay, so you're sharing an environment, and each agent can choose to do an action as a payoff plus 10, but as a minus 100 playoff on the environment. or they can do nothing with 0. So they can get money and then but they do the environment. So each person's going to look at this and say, well, I get plus 10 for my reward, but I get minus 100, so I'm up by, but I only get 100th of that, so it's only minus 1, because my share of the 100th is only minus 1, so I get a plus 9. So each of the agent is going to choose the plus 10, but then what happens is you end up with each one gets the minus 100 payoff, so you get 100 times 10 plus minus, if it's 1,000 minus 10,000, it's 100 times 100, so 100 players get minus 100, so you get minus 9,000, whereas if no one did anything, you'd end up with a 0. Okay, so in this zone here, the only Nash equilibrium is everyone destroys the environment and everyone is worse off. Whereas if they'd all just done 0, they could have got nothing. They could have done this. So everyone acting greedily is bad for the environment. So this is the environment of that. So for each action, doing the action has a payoff of 9. And if every agent does the action, so every agent can think for itself, it's better off for them if they do the action. But overall, you're all much worse off, even dividing by the 100th of this. All right. So let's now look at some examples of some Nash equilibrium. So think about what are the Nash equilibria of this game. So Andy gets to either keep, share, or give. Hint, there's more than one Nash equilibrium here. Maybe we'll pause here and then we'll come back next time. So think about what the Nash equilibria for this game are.